Hello, and welcome to the continuation of our discussion of series solutions. So why will this power series method work in general? The answer is a theorem due to Fuchs. Suppose that a0, a1, and g are real analytic functions on the interval I, and suppose that f is a solution of the ODE f double prime plus a1 of x times f prime plus a0 of x times f equals g of x on the interval I. Now we know this differential equation has a solution because a0, a1, and g are real analytic and thus continuous. So the existence of the solution is not a problem here. But what is neat is the following property. This solution f is also real analytic on I. And moreover, we know something about the interval on which its power series expansion at a point in I will converge. The radius of convergence of the power series of f centered at a point x0 in I is at least as large as the radii of convergence of the power series for the three coefficient functions a1, a0, and g centered at x0. So not only does having a0, a1, and g being real analytic tells you that f is real analytic, but if you know stuff about the power series expansions of a0, a1, and g, you will also know more stuff about the convergence of the power series for f. Let's illustrate this with an example. We'll solve a version of Airy's equation, f double prime plus x times f equals 0 with the power series onsets. So why can we do this? The coefficients here are a1 of x equals 0, a0 of x equals x, and g of x equals 0. It's hard to find simpler coefficients, I think. These are real analytic functions on R, and their power series, if you center them at x equals 0, or x equals anything, will converge on all of R. I mean, after all, these coefficients 0, x, and 0 are polynomials. So this tells us that the solution to Airy's equation has the form f of x equals sum from k equals 0 to infinity of ak times x to the k. That's a power series expansion for f centered at 0. And moreover, this series is going to converge for all numbers x on the real line. So we just have to figure out what the coefficients ak are. And we'll do that, of course, by differentiating and substituting into the equation. So we'll start with f prime of x is the sum from k equals 1 to infinity of k times ak times x to the k minus 1. And f double prime of x equals the sum from k equals 2 to infinity of k times k minus 1 times ak times x to the k minus 2. These are just our familiar formulas for differentiating power series. We'll substitute these into the ODE, we'll combine some things, we'll reindex, and we'll figure out what the coefficients ak are. So let's get started. 0 is f double prime plus x times f. I put the two power series in. I have the power series for f double prime, that's the sum from k equals 2 to infinity. And then I have x times the power series for f. And I won't do anything to this first power series, the sum from k equals 2 to infinity just yet, but I will move that x inside the second power series. So now that's the sum from k equals 0 to infinity of ak times x to the k plus 1. And now I want to reindex and combine the series in a couple of ways. I want to have the same powers of x in both series. I like powers of plain old x to the k. And I want to get the series starting at the same index. You see, one of these series starts at k equals 2 and has powers of x to the k minus 2. The other starts at k equals 0 and has powers of x to the k plus 1. So in the first series, I start my sum at k equals 2. I want to bring that down, say, to starting at k equals 0. So every time I see a k, I'll bump it up by k plus 2. So k goes to k plus 2, k minus 1 goes to k plus 1, ak becomes ak plus 2, x to the k minus 2 becomes x to the k, and I've started my sum at k equals 0. In my second series, I want to get to powers of x to the k, and I have k plus 1s here. So I will increase the starting index to k equals 1, and inside the series, I'll subtract a 1 off from my k's. So ak goes to ak minus 1, and x to the k plus 1 goes to x to the k. So now in both series on this third line here, the power is x to the k. But the second series starts at k equals 1, and I want both series to start at the same index. So in the first series, which starts at k equals 0, let me just break off and write explicitly that k equals 0 term. If I take k equals 0 here, I get 2 times 1 times a2 times x to the 0. That's a 2a2. And then I start my series now, sum k equals 1 to infinity, k plus 2 times k plus 1 times ak plus 2 times x to the k. And I keep my other series as it was, sum k equals 1 to infinity of ak minus 1 times x to the k. And now I can combine these two series into one because they have the same powers x to the k in each. So I have 2a2 plus the sum from k equals 1 to infinity of this big coefficient k plus 2 times k plus 1 times ak plus 2 plus ak minus 1 times x to the k. Now this line here, this fifth line in our calculations, this is itself a power series. I have the k equals 0 term, the 2a2, and then I have x, x squared, and so on, all in this sum here. And I know that this power series adds up to be 0 for all values of x. And so we can use the identity principle to tell us about the coefficients here. Namely, 0 is equal to 2 times a2, and it's also equal to the coefficient inside the sum from k equals 1 to infinity. 0 is equal to k plus 2 times k plus 1 times ak plus 2 plus ak minus 1 for k greater than or equal to 1. So this immediately tells us that a2 equals 0, and we get a recursion relation for ak plus 2. Now ak plus 2 is minus ak minus 1 divided by k plus 2 times k plus 1, and that's valid for k greater than or equal to 1. So what's interesting here is that the recursion relation tells us what ak plus 2 is in terms of the coefficient ak minus 1. In other words, a coefficient 3 down the line from ak plus 2. And because this recursion relation is only valid for k greater than or equal to 1, this is really going to tell us about a3, a4, a5, and onward. So we know a2 equals 0, and this leaves a0 and a1 undetermined by the recursion relation. This is not a problem. We have a second order ODE here, so we expect and we want two free parameters in the end, and that will be a0 and a1. And now we want to try to figure out a better formula for ak plus 2, a formula that depends just on k, not just on the preceding values of ak. So we'll calculate ak plus 2 for some values of k that are small and see if we can get a pattern to emerge. And we're going to do this for quite a few numbers k because it takes a little while to see the pattern. So a3 is a1 plus 2, and that's going to be minus a1 minus 1 over 1 plus 2 times 1 plus 1. That's minus a0 over 3 times 2. a4 is a2 plus 2. That's minus a2 minus 1 over 2 plus 2 times 2 plus 1. That's minus a1 over 4 times 3. So we see already our undetermined coefficients a0 and a1 appearing here. a5 is a3 plus 2. That's minus a3 minus 1 over 3 plus 2 times 3 plus 1. That's minus a2 over 5 times 4. And ooh, that is 0. a6 is a4 plus 2, which is minus a4 minus 1 over 4 plus 2 times 4 plus 1. That's minus a3 over 6 times 5. That is a0 over 6 times 5 times 3 times 2, using the formula for a3. a7 is a5 plus 2. That's minus a5 minus 1 over 5 plus 2 times 5 plus 1. That's minus a4 over 7 times 6. Using the a4 formula, that's a1 over 7 times 6 times 4 times 3. a8 is a6 plus 2, which is minus a6 minus 1 over 6 plus 2 times 6 plus 1. That's minus a5 over 8 times 7. That is 0 from the a5 formula. a9 is a7 plus 2, which is minus a7 minus 1 over 7 plus 2 times 7 plus 1, which is minus a6 over 9 times 8, which is minus a0 over 9 times 8 times 6 times 5 times 3 times 2. a10 is a8 plus 2, which is minus a8 minus 1 over 8 plus 2 times 8 plus 1, which which is minus a7 over 10 times 9, which is minus a1 over 10 times 9, times 7 times 6, times 4 times 3. a11 is a9 plus 2, which is minus a9 minus 1 over 9 plus 2 times 9 minus 1, which is minus a8 over 11 times 10, which is 0. And hopefully you are still awake after all these calculations, but I think we start to see a pattern emerging. And it seems to emerge in threes. We can write any number k in the natural numbers uniquely as k is equal to 3 times j, or k is equal to 3 times j plus 1, or k is equal to 3 times j plus 2 for unique non-negative j. And this is just division by 3. What is your remainder when you divide an integer by 3? 0, 1, or 2. So the pattern in the previous slides suggests that a3j plus 2 is always 0. And if you stare deep into the heart and soul of the patterns for a3j and a3j plus 1, you're going to get the following formulas. This is a little complicated, so bear with me and let me write out some preliminary material. I'm going to define two numbers, alpha 0 and beta 0, to be both 1. And for j greater than or equal to 1, I'm going to define a number alpha j to be the following number, minus 1 to the j over the following product. 3j times 3j minus 1, then jump down to multiply by 3j minus 3 times 3j minus 4, then keep jumping down by 2's until you multiplied through 6 times 5 times 3 times 2. And you may want to hit pause here and calculate aj for a few small values of j, and see if you start getting numbers that you saw on the previous slides. You should. And similarly, we'll put beta j to be minus 1 to the j over 3j plus 1 times 3j times 3j minus 2 times 3j minus 3. We'll keep dropping down to 7 times 6 times 4 times 3. It's like we keep subtracting down by 3's and multiplying pairs here for alpha j and beta j. And again, hit pause, go back to the previous slides, calculate some alpha j's and beta j's, and see if you're getting what we saw before. Then, here's the pattern that emerges for our coefficients a3j and a3j plus 1. a3j is equal to a0 times alpha j, and a3j plus 1 is equal to a1 times beta j. So we know that our coefficients ak are going to be one of three things, a3j, a3j plus 1, or a3j plus 2. I'm saying a3j plus 2 is always 0, and I'm telling you what a3j is and a3j plus 1 is in terms of this new number alpha j and beta j, as well as the arbitrary coefficients a0 and a1. Now remember what Fuchs's theorem says. This area ODE, f double prime plus x times f, has a solution, f of x, which is the sum from k equals 0 to infinity of ak times x to the k, and the series is going to converge for all real numbers x. So here's what we can do. We can rewrite f in a nice way based on how all these coefficients fall out. We have f of x is the sum from k equals 0 to infinity of ak times x to the k. I claim from some deeper series theory that I have in the notes that this is really equal to a new sum. This is the sum from j equals 0 to infinity of a3j times x to the power 3j plus a3j plus 1 times x to the power 3j plus 1 plus a3j plus 2 times x to the power 3j plus 2. And if you don't want to look into the appendices to verify that, I don't blame you, but instead you could just look at this series in j and start calculating it for some small values of j. J equals 0, j equals 1, j equals 2, and very quickly you'll see that we start filling in by 3's all the possible values of ak times x to the k. Now we know something nice, that a3j plus 2 is 0, so we can just delete that term from the stuff in parentheses. So f of x is really the sum from j equals 0 to infinity of a3j times x to the 3j plus a3j plus 1 times x to the 3j plus 1. And now I claim that this is really the sum of two series, sum j equals 0 to infinity a3j times x to the 3j plus sum j equals 0 to infinity of a3j plus 1 times x to the 3j plus 1. I mean, what else could it be? Well, we need some assurance that this series over the 3j's and the other series over the 3j's plus 1's, that both of those series converge separately. Otherwise, how could we get this last equality of breaking the 1 series over j into the series over the 3j and the series over the 3j plus 1? This, I claim, follows from some more technical theory, which you are welcome to read if you want in the appendices or not. But the point is, because we go back to Fuchs's theorem, assuring us that this series for f converges for all x, we're able to do this decomposition and breaking apart ultimately into these two series, 1 over the 3j's, 1 over the 3j plus 1's. And now we know what a3j and a3j plus 1 are. So really f of x is the sum from j equals 0 to infinity of a0 times that special number alpha j times x to the 3j plus the sum from j equals 0 to infinity of a1 times that special number beta j times x to the 3j plus 1. So now let's define two new series. It looks like f of x is the sum of a scalar multiple of one series, a0 times the alpha j series, and a scalar multiple of another series, a1 times the beta j series. So put fancy j1 of x to be the sum from k equals 0 to infinity of alpha k times x to the 3k, and fancy j2 of x to be the sum from k equals 0 to infinity of beta k times x to the 3k. Then all the work above, plus the technical convergence theory that I'm not going into right now, says that f of x is a0 times j1 of x plus a1 times j2 of x. So here, a0 and a1 seem to be arbitrary. We couldn't figure out anything about them from the identity principle, and it looks like we've written f as a linear combination of two different functions, j1 and j2. And of course, this is what we expect for a second-order equation. We should be able to write it as a linear combination of the two functions in the fundamental solution set. And let's probe this a little further. You might ask, can a0 and a1 really be arbitrary? Or at least I'm asking this of myself because it's the sort of thing that keeps me up late at night. We didn't find restrictions on their values, but maybe we missed something along the way. And for that matter, do these functions j1 and j2 form a fundamental solution set for the operator a on f, which will be defined to be f double prime plus x times f? We know that this operator a, this array operator, when you apply it to the sum a0 j1 plus a1 times j2, we know that's going to be equal to 0, because we know that f solves Airy's equation and f has this form, f equals a0 j1 plus a1 times j2. But just because a linear operator hitting a sum of vectors equals 0 doesn't mean the linear operator hitting the vectors individually equals 0. So do we have a on j1 equals 0 and a on j2 equals 0? We're going to answer both questions affirmatively. And the trick is to look at an initial value problem. We were just solving an ordinary differential equation, a nice homogeneous ODE, but now I'm going to put some initial values in. Say we try to solve the initial value problem f double prime plus xf equals 0, with f of 0 equals 1 and f prime of 0 equals 0. We know there is a unique solution to this initial value problem just by our existence theory from earlier in the course. And Fuchs's theorem tells us that this solution f has to have a power series expansion centered at 0, which will converge for all x. So we can write f of x as the sum from k equals 0 to infinity of ak times x to the k. And in particular, we know what some of those coefficients are. Because this is an initial value problem, we know 1 is equal to f of 0, and f of 0 is the number a0, and 0 is equal to f prime of 0, and that's the number a1. So the work that we had done before also allowed us to write f of x equals a0 times j1 plus a1 times j2. But here, a0 is equal to 1, and a1 is equal to 0. So this means that our solution to this IVP is really f of x equals j1 of x. So what does that tell you about j1? j1 is equal to f, and f solves Airy's equation. So a on j1 is equal to 0. The Airy operator on j1 equals 0. So j1 by itself is a legitimate solution of Airy's equation. And the same for j2. You'd look at the initial value problem f double prime of x, plus x times f equals 0, with f of 0 being 0 this time and f prime of 0 being 1 this time. And then I'll show you that the area operator A on J2 is also equal to 0. Great. So we're halfway to having a fundamental solution set. Are these functions J1 and J2 linearly independent? That's the next thing you need to know for a fundamental solution set. Well, we know that A on J1 equals A on J2 equals 0. J1 and J2 both solve a differential equation, so we just have to check the Wronskian. And it suffices to show that the Wronskian of J1 and J2 at 0 is not 0. And remember what the Wronskian is. This is J1 of 0 times J2 prime of 0 minus J2 of 0 times J1 prime of 0. So can we calculate what these values at 0 are for J1 and J2? And I'm picking this Wronskian to be evaluated at 0 because I know that J1 and J2 are basically power series centered at 0. So I know a lot about their values at 0. Okay, so J1 of x we said was the sum from k equals 0 to infinity of alpha k times x to the 3k. And if we expand this out a little, this is going to look like alpha 0 plus alpha 1 times x cubed plus what I'm calling order 6 terms here. These are terms that have a power x to the 6 or higher in them. And J2 is equal to the sum from k equals 0 to infinity of beta k times x to the 3k plus 1. So this will look like beta 0 times x plus beta 1 times x to the 4 plus terms that have a power x to the 7 or higher in them. And so just from these power series, we can read off that J1 of 0 is equal to alpha 0, which we define to be 1. J1 prime of 0 is equal to 0. J2 of 0 is equal to 0, and J2 prime of 0 is beta 0, which is equal to 1. So the Wronskian for J1 and J2 at 0 is going to be 1 times 1 minus 0 times 0, which will be 1, which is non-zero. So the Wronskian at 0 is indeed non-zero. J1 and J2 are linearly independent solutions of Airy's equation. They form a fundamental solution set for this homogeneous Airy's equation. We've found our fundamental solution set via power series ansatz. We are done.